So the higher order takeaway here, though, is when you get to step 2, the point is you want to change code into some graphical structure, some structure in computer science that either exists or we invent. And the reason why we want to do that is then we can ensure that we are walking all of the code and we have some degree of confidence for exhaustiveness. Right? There are these two things that we tend to talk about when we talk about mathematical theory or computer science theory, and those things are soundness and completeness. Something that is sound is essentially shown to be logical, that it is correct from a perspective of logic, reason, analysis, something of that nature. However, things that are sound, by just soundness alone, don't say anything about completeness. So, for example, you could have, let's say, an if statement inside of this function and say this if statement is logically sound, like it's doing the right thing, but it doesn't say anything about the rest of the function. And so oftentimes the second property that you want is completeness, that you show that this algorithm or this equation is sound and complete. So it's really, I think it can be 4 things. It can be sound and complete. It can be sound and incomplete. It can be unsound and complete, or it can be unsound and incomplete. So the 4th case is kind of, you don't really ever want to be there, because I don't know that you're really adding much if it isn't sound and it isn't complete. But the other 3 all have value. The one that obviously is like the golden prize is the one where it's both sound. It has soundness and it has completeness. But usually for really hard problems, you generally can't have both. And I'm not saying that you can't ever, but again, science, trade-offs,